Forget everything the movies showed you. The real science of falling into a black hole is not just more extreme, it is something the human mind was never designed to understand. It involves a paradox that has divided the greatest physicists alive for 50 years. Imagine two clocks, one strapped to the wrist of a falling astronaut, the other ticking far away, safe from the black hole's pull. As the astronaut drifts closer to the event horizon, her own watch keeps steady time. Seconds pass. Heartbeats remain regular. But for anyone watching from a distance, everything changes. Every signal from the falling astronaut takes longer to arrive. Her image slows, colors fade to red, and her final moments seem to stretch toward infinity. In the language of physics, this is the difference between proper time, the time she lives through, and coordinate time, the time measured by a distant observer. The Schwarzschild solution tells us that while the infaller crosses the horizon in a brief, finite moment, the outside world sees her slow to a crawl, never quite vanishing from view. For a stellar black hole 10 times the mass of the Sun, the event horizon is only about 30 kilometers across. For the monster at our galaxy's center, Sagittarius. A star, the horizon is 12 million kilometers wide. No matter the size, the split between what is experienced and what is seen is absolute. The universe itself seems to disagree on what is real. Gravity is not uniform near a black hole. As you fall, the force pulling on your feet is stronger than the force on your head. This difference is known as a tidal force, a stretching that grows sharper the closer you get. The key lies in the tidal gradient, set by the equation G times m divided by r cubed. For a black hole with a small event horizon, the numbers become extreme. The smaller the horizon, the more violently gravity's grip changes from head to toe. For a 10 solar mass black hole, the region where these forces become deadly lies thousands of kilometers outside the horizon. But scale up to a supermassive black hole, and the same gradient drops off. The event horizon swells to millions of kilometers, and the tidal forces at its edge become surprisingly gentle. The difference is not just a matter of size, it is a matter of survival. The closer you get, the more the gradient decides your fate. The body is not built to survive a black hole's tidal forces. For a 10 solar mass black hole, the difference in gravity between your head and your feet spikes to about 20 million meters per second squared, 2 million times Earth's gravity. Bone, muscle, and sinew stand no chance. Even before reaching the event horizon, the stretching force would pull you apart, cell by cell, faster than you could register the pain. The process is so abrupt that from the moment the tidal gradient crosses the lethal threshold, less than a second remains before complete disintegration. But scale up to a supermassive black hole, like the one at our galaxy's center, and the numbers collapse. At the horizon, the same tidal difference drops to just 0.02 of a meter per second squared, barely a gentle tug. You could cross the horizon and feel nothing at all. In Kip Thorne's words, stellar mass holes tear you apart. Supermassive holes let you glide through the horizon harmlessly. The physics is merciless but also specific. Whether you are shredded or spared depends entirely on mass. For some travelers, the crossing is a moment of ultimate violence. For others, it is a silent glide into the unknown across the horizon. Inside the event horizon, every possible path leads only deeper. No force, no signal, not even light can escape. The equations of general relativity predict that as you approach the center, space-time itself begins to twist beyond recognition. The curvature grows without bound. Mathematically, it heads toward infinity. No known law of physics can describe what happens at this point. For the falling observer, the journey from horizon to singularity takes a finite amount of proper time, measured in seconds for a stellar mass black hole or hours for a supermassive one. But at the singularity, the very fabric of reality tears apart. Causality breaks down. Every theory we trust, including gravity, quantum mechanics, and the rules that govern the universe, fails to give answers. the black hole's core is a boundary not just for matter, but for knowledge itself. Stephen Hawking's calculations in the 1970s revealed something deeply unsettling. Black holes are not perfectly black. Over unimaginable timescales, they radiate away their mass as heat, a process known as Hawking radiation. But this prediction created a crisis. According to quantum mechanics, information about the past must always be preserved, a principle called unitarity. Hawking's evaporation seemed to erase that information forever, violating the very rules that underlie quantum theory. Leonard Susskind, in a 2015 lecture, captured the dilemma when he said, "Inside the hole you feel smooth. Outside, the same physics lives on a holographic skin that slowly releases the data." Don Page, Hawking's student, showed that if black holes obey quantum rules, their entropy peaks halfway through evaporation, then falls as information leaks out. This is the Page curve. But no one agrees on how or even if information escapes. For decades, Hawking struggled with this contradiction, and the paradox remains unresolved. The laws of physics themselves seem to break down at the edge of a black hole. Hawking radiation is not a quick escape hatch. For a black hole 10 times the mass of our Sun, the predicted evaporation takes more than 100 million trillion years. That is time enough for every star in the universe to burn out and fade. Even the supermassive black hole at the heart of our galaxy would outlast the cosmos itself. The mechanism, as Hawking described it, starts with pairs of quantum particles flickering into existence at the horizon. One falls in, the other escapes, draining the black hole's mass bit by bit. But what happens to the information carried by everything that ever crossed the horizon? Does it leak out, encoded in the radiation, or vanish forever? No one can say. The paradox remains, and with it, a boundary to what we can know. Black holes do not just swallow matter, they swallow certainty. A black hole is not just a cosmic vacuum cleaner. It is the place where our understanding of reality ends. And somewhere out there, one is waiting. Subscribe to Quantum Lens, because the universe is stranger than we ever imagined.